So this is an exponential model. The difference here is that we have the number e as the base, and it's a little different model than what we're used to. With this model, the decay rate is right here. So our decay rate in this example is 0.003, and that's 0.3%, a negative 0.3%. So the population is decreasing, and this is unusual. As I mentioned, there are a few other countries, Germany being one of them, that has a population rate that's a negative. It's declining versus growing. So this is a population that's decreasing. And then we had this in because one of the classes we're going to miss is called data fitting, and because of the snow days. So if you were looking at this scatter plot, and this is the data, which of these three models do you think you would use to try to fit this data as a model? Would you use logarithmic, exponential, or linear? Exponential, okay. What did you say, Di? Well, the log function would not be a very good function for this, but either an exponential or a linear would be a good fit. The exponential is a little bit better. The reason why a log function isn't good is, remember, your log functions, if we start, we wouldn't be looking at negative values, but your log functions go through 1, 0, and they grow fairly rapidly, and then their rate of growth starts to decline like this. It's still growing, it just gets smaller. And as you can see here, whereas our exponential growth rate starts off slowly and then zoom, goes up like that. Notice they're inverses of each other. So this data, if you look at, if you were trying to fit something between here, you can see that it starts off, the growth of the video in millions of dollars is fairly slow, but then when we're getting up to these later years, it's growing quite a bit. Now, just to show you, not that we have to do this, I put this into the calculator, and when you're comparing models that are bigger than linear models, I ran a linear regression on this in my graphing calculator and an exponential regression. And you can see both of them are very good fits. The R-square value is almost 0.98 with an exponential model and 0.93 with the linear. So that's good. And if you look at the scatter plots, the line goes through and is really close. It looks like it goes right through this first point here. And it's really close to the other one. So it's not a bad model at all. But notice your exponential is even a tighter model. So either one of those answers would be appropriate for this. And if you use these models that are given right here, notice here the exponential model looks like this. Y equals, your coefficient is, let's call it 65.8. Your base is 1.6178 to the x. So this shows your growth rate is 6178, which is about 61.78%. That's, as Mr. Sanders says, huge. All right. And then our linear model here, 155.9, and that's in millions of dollars, don't forget, is the slope. The intercept doesn't make any sense here unless we're thinking about business and being in the hole at the beginning of time, in terms of you're not making any money, you're going to have your capital expenses and all that. So these would be the two models, and if you were trying to figure out like how many videos they may be sold. Now, for all I know, after 2010, maybe nobody bought this video anymore. Maybe they came out with a new video and people stopped using this, just like many things in technology today. If you go too far out in the future, your model could be really bogus because something new comes out, and that's where the excitement is. Nobody buys these older videos anymore. Yep, just like the iPhones, right? So those are your warm-up activities. So let's take a look at the class demo today. The class demo, we're going to be, again, looking at exponential growth and decay models. But because we're going to be looking at problems in context now, we're not going to be looking at the parent functions, which are just models that look like this, b to the t. Now we actually have transformations of this model, because often we're starting with some number of either numbers of cells, numbers of people with a virus, a certain population, the number of square miles of rainforest before destruction. I mean, there's lots of in context problems for exponential growth and decay. So because there's a context, there's always some type of number out here that's your initial value. Now, notice I've called these functions A of t. They could be called P of t if I'm dealing with populations. So the symbol I would use here might be P sub naught for the initial population. If I'm looking at the amount of money that's growing, I might look at A of t equals A sub naught. If I'm looking at a quantity like the number of bacteria that's growing in a petri dish, I might say Q of t and have a Q sub naught here. If I'm looking at the mass of an object, which we're going to be looking at shortly, and how it's declining, I might have little m of t equals m sub naught. So the letters don't matter. Those are perfectly your choices. What's important here is that you see I'm giving you two equivalent forms, so that these two equations will give you exactly the same answer. So let's take a look at how these two equations are equal. So if we say A of t equals A of t, I want you, you don't have to write this down. I just want you to see why these are equivalent. Then the first A of t is some initial value times our base to the power of t. And our base could be a number bigger than 1 or a number between 0 and 1. It's either growth or decay. And this is what we're used to seeing. If you recall from our homework and our book work, we also looked at the base of e, which is a special number, and that represents continuous growth. So whenever we're looking at continuous growth, like with money, continuous compounding in a bank, then e is your base. That's one of the uses for it. And lots of models, we also use e in population growths as well. So how are these two equal? They look really different. Well, one thing you could do is you could divide both sides by a sub naught. And when you do that, that goes away. It's gone. And so then you're left with this equation. So if you notice on both sides, t is the same. So b has to be the same thing as e to the k. So to go from one model to the other, b, your base, has to be equal to e to the k. And that's what this first thing says. For these two equations to be equivalent, b must be the same thing as e to the k. So what if you knew the continuous growth rate? Let's say you knew the value for k, and you were using this model, but you were curious to go back and see what the equivalent model would be. What would be the base? Well, with a little bit of mathematics, which you now know, this is an exponential equation, and we just spent some time learning how to solve exponential and log equations. So this exponential equation, we can solve it for k. And the only way to undo raising something to a power is to perform a log. It's inverse operation. So we can take the log of both sides. Now remember, I told you initially you can take the common log of both sides or the natural log. It doesn't matter. But since our base is e, it's really quite efficient to take the natural log of both sides. So let's take the natural log of both sides here. So we have the natural log of b equals the natural log of e to the k. Now through our log properties, we want to get that k downstairs out of the air, so the k comes down and multiplies the natural log of e. But the natural log of e is just 1, so there's k is equal to the natural log of b. So if you're going from one equation to the other, this would be like your conversion factor. So if you know this value here, k, you can go right over here and find b. Yep. Am I going to what? Wow, shoot, thank you. I'm not recording? Oh, I'm recording. Whoo, scared me. All right. Okay. All right. So we call K the continuous growth rate or continuous decay rate. So if you're reading the problem and it says, and they give you a continuous growth or decay rate, then you know you can go right to this model and put in the value for K. All right. Otherwise, you can find your growth factor, your multiplier, the same way you've always done. You'll be given a rate and you either add it to 1 because it's growing, or you subtract it from 1 because it's declining or decaying. So let's take a look at a real example here. I put this into the lecture with the Ebola outbreak that happened in West Africa. And in 2014, in early September, this was the estimated number of Ebola cases. So that's your initial amount. That's your initial quantity of Ebola cases, because I'm deciding to start recording this data on September 3rd. West Africa, at that point, there's several countries, but these were the 3 countries that the Ebola outbreak was being recorded in. And between September 3rd and November 18th, they grew at a continuous rate of 1.252 per day. Now, I didn't make this up. I actually found some information and recorded this for our purposes. And notice it's per day. You might say to yourself, oh, 1%, big deal. But we'll take a look at what happens with this in a minute. So because it says continuous growth rate, that means you're going to use the formula that looks like this, that has E as its base. Okay, so this is the formula you use because it's continuous. So all you have to do is convert. So we're going to actually do both models just so you can see that they really are equivalent. Sometimes it's hard to believe this. So you're going to be able to see that no matter which model you use, you're going to get exactly the same answer. So let's, in this first column here, put A of t equals A sub naught times B to the t. We'll use that model. And in the second column, let's use A of t equals A sub naught times E to the kt. Okay, and you can go from one to the other. So because my initial information tells me the continuous growth rate, I know that that's the value of K. So in order to make that into a decimal equivalent, I move my decimal point 2 places to the left, and there's my value of K. So I can go right ahead and fill this in right now because A sub naught is 3902. That's my initial number of cases. E is my base. It's a number. It's a constant. And K is 0.01252 times T. So there's the model I would use for the continuous growth rate. Now to go back to my more the familiar model for exponential functions, I have to find B. So over here, I can start to fill this in right away with the 3902, but I have to find my base. And we just found out through a little bit of algebra that B is equal to e to the k. If you look at these 2 equations here, B is taking the place of e to the k. So since I know what k is, I can find B. So I want to find B, and B is equal to e to the k, which is 0.01252. So to find B, I just throw that into my calculator and let my calculator do all the work. So let's quit that and clear all that out. And so let's see, e to the x is right here. So I do second natural log and I get 0.01252, 0.01252. And here's my value for B, 1.012598703. So I'm going to keep that right in my calculator. I'm going to store it under A, store under alpha A. So if I need to use it again, it will be under that, in that storage location. Okay, so I put B as 1.012598703 to the T. And as you can see, 1.0125 is pretty close to 0.01252. This just goes out further. Okay, so if we carried out this percentage further, it would probably look just like this. Okay, because they're equivalent. All right, so let's take a look. Construct two models. We've done that. Here are our two models. And now we're trying to figure out if November 18th was 83 days after this outbreak, when we started recording these number of Ebola cases, how many Ebola cases would be predicted for December 5th if this model was still a good model? Well, we have to figure out how many days after September 3rd, December 5th is. And we know November 18th is our 83rd day. So December 5th is our 100th day. So I would like tables 1 and 3 to use the first model and get an answer and confer that you've arrived at the same number of Ebola cases. And I'd like Abby and Stephen, Jonathan and Rose, and then table 4 to do using the second, yeah, it's after 100 days, right? Okay, so please confer with these 147 people after 100 days. So we're slightly under 4,000 people, and after 100 days, which is just a little more than 3 months, we've more than doubled, almost tripled, right? So actually, we've more than tripled after 3 months. So even though initially a 1% growth rate in this virus didn't seem like very much, the number of people grew, and this is the phenomenal result of exponential growth because it's proportional to your population. So as your population gets big, you're taking that same percentage, but now it's of a bigger number. So what you're adding on is getting bigger and bigger and bigger, and it grows so incredibly fast. And I just wanted to show you the table. Here we are at 100 days, 13,647 people. So if we win every week, so let's go out a week. After 1 week, we're at almost 15,000. And after 2 weeks, we're at 16,000. And at 3 weeks from that point, 17,750. So it's just this virus spreads so quickly. And again, it's a little misleading when we see 1.252% as the growth rate. It seems like it's really small, but as your numbers start to get big, what you're adding on is bigger and bigger and bigger. So you can't be like, you got to kind of change your brain set a little bit, your mindset. Yep. Yep. That's right. Yep.
Is that person the dead people or many?
These aren't dead people yet. I don't have the death rate for that particular Ebola virus. Not everybody died, thank goodness. But this would just be the number of people who have contracted the Ebola virus. Okay. Right. Yes. Mm-hmm. All right. So if we're modeling exponential growth, which we just did with the Ebola virus, the example I used to use was the number of plastic water bottles. And then I would show the video like the last day of the Pacific Gyre, which if you haven't heard about that, look up Pacific Gyre, Gyre. It's really scary. And the incredible growth in plastic water bottles and what it's doing to our environment. So that's just a little environmental issue that if you have some time, free time, and you want to look that up, then what? Oh, I don't know. I don't know. All I know is, oh no, you know what you're thinking of? The little Keurig plastic containers. 9 billion since Keurig has come out, and it will wrap around the diameter, the circumference of the Earth 9 times, I think it was, 9 or 10 times, yeah. That's true. Yep. Okay, really the next most popular topic when you look at any math book and they're talking about the other side of the coin, exponential decay, most books will talk about half-life as an example of radioactive decay as an example of exponential decay. So Jasper, you want to read us the first 2 paragraphs here? let's suppose we use a model. We want to develop a model to determine how much C14 will be present after T years. So if we have a living being or a living object, what percent of C14 is present? 100? Well, this is just percent. What percent if you're living? How much C14 is in you? 100%, right. So if you're alive, all of the C14 is contained in you. Okay. So suppose we have some object and we start with a mass, an initial mass of 100 grams of C14 is contained in it. And we use our exponential model with the only thing we can fill in is 100 times a to the t. So our job is to find what a is. Okay. So we know that after 5,730 years, which is the half-life of C14 is 5,730 years, which means a living thing has 100%, and after 5,730 years have gone by, it will have what percent? 50. And then after another 5,730 years, it will have what percent? 25%, so on and so forth. Okay, so that's how half-lives work. So let's see how we would solve this problem for A, because we want to get the base. So let's see how we could do this. So what we do know about half-lives, is that after 5,730 years, this 100 grams will become 50. So whatever A is, we still don't know what A is, but after 5,730 years, this 100 grams will become 50. So now I have an equation that I can solve for A. Yep, divide first by 100. Yep, because I want to solve for A. So this is what we did on Monday. We want to isolate our factor A to the 5,730. So we have A to the 5,730 equals 1/2. Well, that should be no surprise because it's half-life, right? So now what we're trying to find is the value of A. And the value of A, the base, is going to be this. Well, how do we get a 1 for our exponent? We have two ways. We can raise this thing to its reciprocal 1/5,730, because when you multiply those two numbers, when you multiply your powers, you get 1. Or you could take the 5,730th root, which is the same thing. So it's just easier to write it as an exponent. So this is what I'm going to do. So there's the value of A. It's 1/2, which should be no surprise, 1/5,730. So what this tells us is this is how much it decays each single year, because our numerator is 1 for each year. This is how much it decays. 5,730 is the exponent, and this is the value of A. So I'm just going to go back and plug it into my formula. So my formula looked like this: 100 A to the T. So A is right here, 1/2 to the 1/5,730. And when I use my exponent properties, what do? I multiply these two exponents, so I get T in the numerator. So now f of T equals 100. My base is 1/2, which should be no surprise at all. We're looking at half-life, so each half-life period, it's going to decrease by half. And our exponent is T over the half-life, which in this case was 5,730. So if I put the 5,730 in here, right, because this is T over 1, and when I multiply it, I get T divided by 5,730. So this makes sense, because if T is 5,730 years, this is going to be 1. It's one full period, one full half-life period. Remember, the denominator is grouping your years by 5,730. You're trying to figure out how many half-lives have gone by. So if t is the same as the half-life, then this is 100 times a half to the first power, which is 50. So this makes sense. So in general, this would be the half-life formula we just derived from that simple example. The mass after a certain amount of years or days or seconds or hours, depending on the context of your time, is the initial mass. Your base is 1/2. And then you're just seeing how many of these half-life periods have gone by, which is the number of years divided by the half-life. So that almost makes sense. Then you can convert this. I could do the mathematics and convert this formula to the equivalent formula here, which is continuous. Okay, so which one do you use? Well, whatever your information is that you're given in the example. So if you're using this formula right here and you know the half-life, then R is equal to the natural log of 2 over H. Natural log of 2 is a constant, so this is some number divided by the half-life. That's what you would squeeze in there for the value of R. Okay. Because this negative sign is already there, you might look in some books and not see the negative sign there, and that's because they would give you the natural log of 1/2 here instead of the natural log of 2. That's the only difference. Because remember your log function, between 0 and 1, your natural log is negative. So if the negative sign isn't here, you might see in a book natural log of 1/2 here to make the whole thing negative. But our book has done that for you and put a natural log of 2. So if we were looking at this example, a burial cloth of an Egyptian mummy is estimated to contain 59% of its original carbon-14. How many years old or how long has it been since the mummy was buried? Okay. Probably King Tut. All right. So you can estimate how many years it's been buried, because it's going to start off whenever the mummy was just before it died, it had 100% carbon-14, and after 5,730 years, it will have 50% of the original carbon-14 present. And you're somewhere along here. You're at like 59%. So if you did the calculation and you got an answer like 2,000 years, there's no way you could be right, because 59% is starting to close in on now 5,000 years at least. So just try to get a sense of what your answer is to see if it makes sense. You can always check it. So let's see how we would set up this equation. So our equation says the mass after a certain number of years is equal to the initial amount of carbon-14, which is 100%, which is 1, times 1/2 to the t, which we're trying to find, over the half-life. So some people wouldn't even bother putting in the 1 here because, 1 doesn't do a whole lot. But I want you to see that that says that the initial mass is 100% carbon-14. Now, in order to solve this equation, we need to have a value for the mass after a certain number of years. Well, the mass we're interested in after some amount of time is 59% of the original carbon-14. So I'm going to put in over here 0.59. So that's how much carbon-14 is left. And now I'm going to solve that equation for T. So it's just 0.59. 1, I don't have to bother putting in 1/2 to the t over 5730. So we want to solve for t. And after working on our problems on Monday, we know the only way to undo an exponential function is to take the log of both sides. It's inverse. So I'm going to take log base 10, the common log, or the natural log. It doesn't matter. I'm just going to use the natural log of both sides. So the natural log of 0.59 is equal to the natural log of 1/2 raised to the t over 5730. Why do we use logs to undo, beside the fact that the main reason is that it's the inverse operation, but we get to use the handy dandy log property that says the power rule that takes the power, which is where your variable is located, brings it right down in front and it multiplies, notice in the natural log of 1/2, 5730, times the natural log of 1/2, which is just a number, equals the natural log of 0.59. So you might do this in parts, but you could say I'm going to multiply both sides by the reciprocal of this fraction here. The fraction is the natural log of 1/2 divided by 5730, which is 5730 divided by natural log of 1/2. Doesn't matter, or you can just say I'm going to do this in steps. I'm first going to get rid of the natural log of 1/2 by dividing both sides by that, which is probably where most of you are algebraically at this point. And now you want to solve for t, so you're going to multiply both sides by 5730, which just multiplies the natural log of 0.59 over the natural log of 1/2. And that's t. So if I put this in my calculator, I'm expecting some number of years, at least close to 5,000. So let's put it into my calculator and see what I get. So we'll move it over. Clear everything out here. Quick. All right, so notice my natural log button is right here, 0.59. I multiply that whole thing by 5,730. And then because my calculator knows order of operations, I don't have to worry about parentheses. I divide by natural log of 1/2. And there I am, approximately 4,362 years. And that makes sense. Okay. So that's how you would use the half-life formula for a problem using carbon-14. If you wanted to use the other equation, which is m of t equals m sub naught e to the negative RT, you'd have to know what R is. And if you, yep. Yeah, round off to the whole number, yeah. So R, how to go from R back to, how to get the value for R when you only know the half-life is you just take the natural log of 2. So R is equal to the natural log of 2 divided by the half-life, 5730. So you throw that in your calculator. Natural log of 2. Yep. Divided by your half-life. That will give you your value of R, your continuous decay rate. Notice it's 0.000. There's 3 zeros because that's -4. 1, 2, blah, 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 blah. So R equals 0.000120968. I'm going to round it off a little bit. So M of T equals 1 because I had 100% carbon-14 minus, and then I put as much of this in as I can because I want to have an accurate answer. So if I were solving this problem, this is how I would set it up. And I would just solve for t using the same methods we just did a minute ago by taking the natural log of both sides, and then you would be dividing by this huge number, and you would get t. Okay.
Is half-life always 5,000?
Oh, wait a minute. I made a mistake and nobody noticed. This is supposed to be E here. E to that number. Go ahead, Mahendra.
Is half-life always is 5,000?
For carbon-14. Yeah. Half-life for different elements can range from really short amounts of time, like seconds. Think about drugs in your body. They all have different half-lives. Or they can be millions of billions of years. And that's one of the problems with nuclear power generation is the nuclear waste. The various isotopes of plutonium and uranium have huge half-lives. There's no way any container that we construct right now will last the number of years needed to contain that nuclear waste. So that's part of the issues that we have with nuclear waste disposal. Okay, so you have quite a few activities, or actually like 3 or 4 that will help you. And I do want to point out one thing. Oh, shoot, I forgot about logistic growth. Hang on. This you want to put will be on final. I'm giving you a hint. Final exam, this model. Okay, so who has a nice booming voice? Ramses? All right. Read logistic growths for us. Environment. The planet Earth is a closed environment. Any amount of space that doesn't continue to grow is a closed environment. You could think of a petri dish with bacteria inside of it. The bacteria would start to grow because there's lots of space, lots of nutrients in the petri dish, and then everything starts to decline and decrease, and we're growing, but we're growing much slower, and then we run out of space, so there's a limit. Okay, so what do you, just quickly looking at this, what sort of things come to your mind as you look at this particular model for logistic growth? What comes to your mind? What do you see? Jasper? Yeah. Yeah, it looks like almost two different curves. Like this first curve, the blue part looks totally exponential, right? It's still continuing to grow, but then it slows down. So this almost looks like a log problem. So it's exponential at the beginning. It continues to grow, but then your growth rate is slowing down. Notice if you drew a straight line right beside the curve right here, it would be pretty steep. And if you drew a straight line that touched this curve up here, it would be not as steep. So the growth rate is declining. Okay. What else do you notice? How would you describe the shape of that beside two pieces? Does it look like a letter? Huh? It looks piecewise, but what letter does it look like? F? Oh. How about another letter? S. Yeah, this is called S shape. S, it's an S-shaped curve. The real name, you don't have to know that, is sigmoidal. Ooh, sigmoidal. Okay. And these two things right here are important to know. This point right here in calculus is called an inflection point. And this actually, you can figure out this value. There's a formula for this. It's where your graph, for those of you who had a little calculus, goes from being concave up to concave down. It's the inflection point. We can't do it right now with the math that you know. I'm just saying there is a formula for it. Okay, so notice up here we have this green dotted line. That's our horizontal asymptote, and that's the ceiling. That's the limit of our growth. And that line right there is y equals c, and the c is located right here in the model. Your numerator is c, and they use the big capital C because it stands for what's called the carrying capacity of your environment. It's sort of the maximum limit on your growth. So if you try to figure out, or you try to find a book on the carrying capacity of planet Earth, you will see a range from 10 billion to 30 billion. Those, and as you can see, nobody really knows. That's a huge spread. So who knows what the population right now is on Earth, approximately? How many? Are we up to 8 billion? You believe it? Well, all you have to do is go online, and it has like a running calculator. So if it's really up to 8, then the first limit of 10 billion is not too far away. Oh, is there? Yeah. Okay. Well, it's a model. All right. So here's the type of thing you'll probably see on your final, although you'll be able to see these numbers really clearly so that you wouldn't necessarily have to work with the formula. You can read the values right off of the graph. But this is right out of your book. It's example 3 on page 498. I put this in through GeoGebra. As you can see, this is an S-shaped curve. I want to also point out to you, if you are like into natural parks, we reintroduced bison into Yellowstone National Park. And these are just the years 1902 to, oops, that should say 1931. And as you can see, the bison population is starting out exponential, and now it's going to start to be logistic. It's a nice real life representation of a population that can be modeled with logistic growth. If you're trying to grow the population, yeah, well, that is buffalo. Bison is AKA buffalo. American bison is buffalo. Yeah. Okay. So let's see how we'd answer this question. How many people became ill with the flu when the epidemic began? So what do I substitute in for T here when I want to know when the epidemic began? What value of T do I put in here? 0, right? Because we're looking for the initial amount. So if I were going along, I'm not going to get scared about this formula because everything's filled in for me. The only thing I have to put in here is the value of 0 for T right there in the denominator. And I'm still not going to get nervous because I have my calculator and I'm feeling confident about my math abilities, and it's e to the 0. And what's e to the 0? 1. Thank you. So it's 1 plus 20. So this is going to represent the initial number of people right there. That's my model. So let's throw that in to my calculator. And let's see how many people were initially affected, or at least when I started to record this. So 30,000 divided by 21 is about 1,429 people. 1,429. Where would this appear on my graph if I didn't do the calculations and I wanted to try to estimate it from my graph? Where would that value be on my graph? The y-intercept, exactly. Right here. So that value would be located right here. When time is 0, we have approximately 14,029 people ill. Okay. All right. So how many people were ill by the end of the 4th week? Well, if we had a really nice, I could read the information right off my table. I'd put a line right through 4, and I'd come over and see what the value was at that particular point. Okay, that's how I would use my graph. How I would use my model is I would do the same thing I just did in A, but instead of putting 0 in for time, I would put in 4. And you can all figure out that answer later. Okay. Here's a nice question of the hour. What is the limiting size of the population that's going to become ill? What's the most number of people that can become ill? 30 grand, it's right here. This is your carrying capacity, which is 30,000. And if you just you didn't even have the formula available to you, and you just had your graph, you're looking at this value right here for your horizontal asymptote, which is there's 30,000 people. Okay. Cutter, which is how you say Q-A-T-A-R. It's really pronounced as Cutter. This has an annual growth rate. Look at the value of B of 11.2%. It's like a postage stamp. It's a little part of the peninsula in Africa. You should look this up, how small this is, and look up its area. Compare that with China's growth rate, which you'll be able to get once you work through this. And once you identify which one of these is China and which one of these is Qatar, you're going to see that after like 30 years, the population in Qatar will outgrow China's population, which is totally impossible when you look at the size of Qatar. Okay, and the only reason I picked Qatar is because the Olympics are going to be there, not this summer, but I think they're actually having a Winter Olympics here, which doesn't make sense. Huh? Is it FIFA World Cup? I think both.